Hello, everyone. Thanks for coming to the last talk in the kernel track. I am also one of the track runners, but I am also the closing talk in this track. And my name is Anita Zhang. I am technically a software engineering manager at Meta. Officially, I am Engineer D, Manager D. That is my title in Workplace. And I support what I call the Linux umbrella family of teams. But today I'm just going to talk about one of them, Linux Userspace at Meta. So if you saw this talk at All Systems Go or you saw a recording of it, this is pretty much the same talk, maybe with a little more details here and there and some updates because it's been like 6 months since that talk. I'm going to talk about what is Linux Userspace at Meta, talk about some of the things we've done in systemd in the past couple of years, and then move on to some of the Linux distribution related stuff before closing with some of the things that we're doing in BPF. Oh, if you have any questions during the talk, I'd prefer if you wait till the end to ask them. Okay, so what is Linux Userspace at Meta? The whole philosophy behind the Linux-related teams at Meta is that we are upstream first. We have some hyperscaler problems that I think other folks are also interested in finding solutions to, and also other companies also have solutions, problems. So by coming together, we can kind of work on a general solution in like a well-established project that we can all benefit from. So the Linux teams at Meta specifically, I'm referring to the kernel teams. We have a team of a mix of maintainers and contributors to the Linux kernel, as well as the former operating systems team, which I'll talk about in a bit. Yeah. So a brief history of how the Linux Userspace part got started. The operating systems team at Meta, their charter was contributing upstream and building community. They focused primarily on Chef, which we use to update all of our fleet of bare metal hosts. And they also supported CentOS, which is the Linux distribution that we use in production. They also supported rollouts of systemd. And they also did upstream packaging, which is bringing in the latest packages from Fedora and related places, and some other stuff. Right before, I guess around the time the pandemic started, there was already some reorgs going in place, but the responsibilities of the team kind of split out into smaller teams with a narrow focus. So a lot of the production support moved to a different internal team, and the open source parts that were left eventually became what we now know as the Linux Userspace team, which is what I'm going to talk about today. So today, we basically still work on Linux distributions and upstream packaging, primarily in Fedora and CentOS, though we also have some contributions in Debian as well, and Arch. We still do a lot of community building, such as these. We come to events and meet with other users of Linux and things like that, as well as maintainers. We still contribute heavily to systemd. We employ a few maintainers of systemd at Meta, though really only like 1 or 2 are active at the moment. And we make we're starting to make more contributions to BPF as the application space. We already have a kernel team that contributes heavily to BPF. And I guess it's not really a meta talk unless we talk about all of the machines that we support. So our teams is mainly focused on the bare metal fleet. So that's the stuff running directly on the hosts and hardware. And of course, we have millions of those. And for the most part, it is a largely homogeneous fleet of mostly for compute, though increasingly, as you know, like with AI, we have more GPU-related hosts as well. For the most part, teams still maintain their own collection of bare metal hosts. we also have a huge pool of shared hosts that most engineers will be running their services in containers, and those end up on the shared pool. On the bare metal fleet, at this point, we're over 98% upgraded from CentOS Stream 8 to CentOS Stream 9. Systemd in particular, we actually deploy as it's released. Next week, we're going to start rolling Systemd 255. We're currently on 253. We're just skipping 254 because of we kind of missed that window during the holidays. If you're interested in Systemd releases in particular, 2 years ago, Don and I did a talk at CentOS Dojo about how we release Systemd in hyperscale. So moving into some of the stuff we've done with Systemd. The first thing I'm going to talk about is Systemd UMD. It is a user space out-of-memory killer that uses cgroups 2, pressure stall information, or PSI, and et cetera, to make kill decisions. This started off as a Facebook incubator project called UMD. The Systemd UMD part of it is just kind of taking the policy and ideas behind UMD and making it work in Systemd. If you're interested in more of the technical details, I did a talk on this 3 years ago at Plumbers. The graphic, you don't have to pay too much attention to it. It exists mainly so I can talk a little bit about how Systemd UMD is different than the kernel killer, for example. So kind of the magic sauce behind Systemd UMD is PSI. So pressure stall information is a way to kind of quantify the amount of time that tasks are stalled. Unlike the kernel killer, which focuses mainly on the amount of memory used and killing the largest consumer, or how fast it was consuming memory and things like that. The thing about PSI is that it only works on cgroups. So I do get a question a lot about whether UMD can support per process killing. And I think just with the way PSI works, that's not really something that we can do in the confines of Systemd UMD. So in Fedora 34, we actually enabled Systemd UMD to be the default user space killer. It actually took multiple versions of Fedora before we kind of reached a configuration that wasn't killing everyone's desktop environment constantly. Sorry. But out of this, we did get some other benefits in Systemd. All of the libraries and stuff that I used to develop Systemd UMD now exist as various knobs in Systemd. So in later versions, you can actually configure and monitor PSI more directly with Systemd without having to use Systemd UMD. And in terms of where Systemd UMD is at Meta, we actually rolled it out alongside the original Facebook UMD. It's taken over a lot of the policy and killing work that FB UMD did before. We mainly keep FB UMD around for experiments. So we have a tool called Senpai that does automated memory sizing tool, automated memory sizing. The thing with memory use is that it's hard to track how much memory an application is actually using. It can allocate a lot of memory, but not actually use all of it. And so Senpai is a way to kind of keep poking a process until we figure out what the working set is. And the other thing we're still experimenting with is profiling before we do an UMD kill. I think that's still requiring tweaks to figure out. The next thing I'm going to talk about is Systemd networkd. So Systemd networkd, it's a daemon that's shipped with Systemd. It's been in there for quite a while already. And it exists to manage your network configurations. As far as I know, not a lot of distributions enable Systemd networkd by default, or they're not using it. But the idea is that you can basically manage your network interfaces with Systemd style configurations. So up until about 2022, Meta was still using network scripts to manage their network interfaces. But network scripts are actually deprecated in RHEL 8. Thanks to our friends at Red Hat, we were able to keep using it up until the end of CentOS Stream 8, basically. But for CentOS Stream 9, we decided to go all in on a more modern network manager. And in this case, we had chosen to go with systemd networkd. Kind of in order to drive home some of the benefits that we're getting with systemd networkd versus network scripts, at least to configure the basic network interface, it's on the network script side, it was a root file and an ifcfg file. For networkd, that's a .network config. If we needed to configure a virtual interface like a bridge or a tunnel, for networkd, that's just adding a .netdev configuration. Network scripts is kind of limited in the number of, or like the types of virtual interfaces you can make, but you just do that in the same like ifcfg file. .link files are a way for you to kind of configure the NIC settings, which in network scripts, we don't have that directly, but we were making a bunch of ETH tool calls in Chef and wanted to kind of drive home that we had a lot of ETH tool calls kind of scattered throughout Chef. And so being able to, centralize it all in a .link file was nice. And then there was a bunch of other stuff like syscuttles that we were also configuring out of band. We had to implement our own custom health checks for network scripts, and also logging that. All that stuff we kind of get for free with networkd. And I guess it's just nice that we don't have to rely on a bash scripts to configure our network anymore. Everyone likes that, right? So systemd networkd at Meta, it is rolled out as a part of CentOS Stream 9. So the 98+% of our fleet, the production bare metal fleet that has CentOS Stream 9, is solely systemd networkd. It took a long time to figure out how to do this safely and verify that, our network wasn't just going to randomly go down. And we've debugged a bunch of things along the way as well. I think the nice thing about like a big scary migration is that everyone just wants to come together and make sure it's done safely. And it was also an opportunity for us to make everything more maintenance friendly, because as with a long-running configuration, you just kind of pile things on over time. So this was a chance for us to clean that up. And of course, we had a lot of support from the other systemd maintainers. Yu Watanabe in particular, he works on networkd, and whenever we had like issues, he helped implement missing features or like give us ideas to fix things. So systemd journald, it's probably the most simple daemon in systemd. It just collects and stores your logging data. It has a lot of metadata in it. The driving question at Meta as to why we ended up working on journald was, could we stop using rsyslog? So at Meta, we still forward our logs directly from journald to rsyslog for storage, because there are a bunch of issues related to like reliability and size of the journal files that we were trying to resolve. Don talked about some of this work at Plumbers in 2022, but basically it covers journal compact mode. This is something he did to lessen the size of journal files, which is nice because it means we write less. He also made various fixes related to Btrfs encryption so that our journal files are much smaller. If you saw Sweet Tea's talk yesterday, you'll know that our fleet is all on Btrfs for the most part. And he also made a bunch of fixes related to like journal file corruptions and things like that. Okay, moving on to the CentOS Hyperscale SIG. So if you don't know what the Hyperscale SIG is, it's a special interest group formed in 2021 and the focus is on making CentOS Stream better for like large-scale infrastructures. What we do there, we can test alternative policies to the CentOS default ones. We released the latest systemd based on Fedora Rawhide and CentOS Hyperscale. So that is also the same version of systemd that we deploy to the Meta fleet. As part of the Hyperscale SIG, there is also a repository called Hyperscale Intel with optimized packages. And we're also using it to deploy RPM copy on write in the Meta fleet. And of course, there's also like a bunch of infrastructure and automation work to make this easy to kind of install and download. There are actually some people who are running CentOS Hyperscale in their personal laptops. And I think Davide actually runs it on his router or something. So moving on to the Fedora Asahi remix. Davide and Neil actually did a talk about this yesterday, but I'll briefly go over some of the work there. So Asahi Linux is basically, the goal is to bring you a polished Linux experience on Apple Silicon Macs. And Fedora Asahi Remix is the official flagship Linux distribution for Asahi Linux. And we're interested in this because it gives you basically a high-performance, reliable, and pretty readily available ARC64 platform. We brought together, we went and got together with all of the community members. It's really nice to see a bunch of motivated people do something really cool with technology. And for us, we actually have a few kernel developers who are using it as their daily drivers. And Yosef actually did a blog post about how he's using Asahi Linux for ButterFS FS tests. Okay, so now I'm going to go over some of the work we did with frame pointers. So first off, what are frame pointers? Assuming you have some knowledge of registers in a processor and also how function stacks work, basically the frame pointer is a register that you can use to point to the start of a function stack. So that makes it really easy to kind of jump up to the stack and basically unwind and figure out how your program executed. This drawing in particular I took from the BPF book from Brendan Gregg. But the thing about frame pointers is that it's optional, right? If you don't compile or you don't make use of the frame pointer, you can use that register for something else, and you save a few instructions when it comes to saving the address of the frame pointer and things like that. So actually, since 2004, frame pointers were not compiled in by default, and this was across many different distributions. So like I said, you get some performance wins, especially when in the days of 32-bit systems, you only had 6-ish registers, and they were only 32-bit in size. Nowadays, you have 16, and they're all 64-bit, so that is less of a problem. And like I said, if you don't compile in the frame pointer, it actually makes it really hard to unwind stacks, which you kind of need for debugging, profiling, and tracing. And Brendan Gregg actually, last night, he posted a really good blog post about the history of frame pointers and where they are now. So frame pointers enabled by default in Fedora. As part of Fedora 38, we at Meta, a few of us got together and decided to kind of make frame pointers, turn them back on by default. And this required a lot of benchmarking and exploration because I think a lot of people were bitten by the performance of frame pointers in the past. And so we had to do a lot of work to make sure that those regressions would not happen, or at least they would be an acceptable amount of regression. So After all that, the steering committee decided to conditionally enable it for Fedora 38 and see where it went from there. Some architectures already had frame pointers enabled by default. A few architectures we omitted because we didn't have them available for testing. And then Python 3.11 in particular had opted out because they saw some pretty huge regressions. But in 3.12, they actually recommend enabling frame pointers, so there were probably some potential fixes and things there. For Fedora 40, the decision was reevaluated, and actually frame pointers are now here to stay in Fedora, hopefully forever. Shortly after the Fedora default, or the Fedora change, was accepted and things like that, Ubuntu 24.04 LTS also enabled frame pointers by default, and recently Arch Linux is also enabling frame pointers by default. So what benefits have we gained since Fedora 38 at least? So Christian, the maintainer of sysprof, he actually rewrote or redesigned sysprof in Fedora 39. And as part of that, he did a couple of case studies. He actually found some, by using frame pointers and his new shiny profiling tool, he was able to fix several performance issues in Fedora, some of which were, at least one of them was in systemd because I stamped his PR, but he, it was a good blog post on case studies of how you can use frame pointers to actually improve performance. Okay, so some of the newer things we're working on with BPF Shiny. I'm going to talk about the first two in a little more depth. But the last three, we actually had some talks about it already. So yesterday, Dan already talked about SCEDX, which is a way to write Linux kernel schedulers with BPF. And then the last one, BP filter, Quentin had a talk last night, and it's a way to speed up IP tables by converting some of the rules to BPF instead. BPF trace, I'm going to glaze over a bit. We only recently started making more contributions again, but probably next year someone will have more stuff to say about the cool stuff we're doing in BPF trace. Okay, so systemd BPFD. This is a new daemon in systemd that is going to be monitoring and auditing BPF programs. This is currently still in review, but I think we have a couple more ideas for detecting issues with loading BPF programs and things like that. This was originally tied to the work with BPF token, which I'm going to talk about next. But I think the issue that people keep talking about is it's not always easy to get observability about BPF. And so that's kind of what systemd BPFD is doing now. And then there's BPF token. So this was merged either end of last year or earlier this year. But the work on BPF token spun out of the need to use BPF inside user namespaces. So I'm sure if maybe a bunch of you have containers and you're like, why can't I use BPF inside my container? Well, it's because of the privilege issue. So with BPF token, you can actually delegate BPF permissions from a privileged process to an unprivileged process, and that will actually allow you to run BPF programs inside containers and user namespaces. And we will actually be working on adding this functionality to Userspace soon, ideally in systemd, but it kind of depends on where the design goes, which is kind of in discussion right now. So that's all I had for today. Linux Userspace wouldn't be where it is without the people that make it happen, and these are some of the people who are on the Linux Userspace team. If you have any questions, you can ask now, or you can contact me at my handles there. No. Thank you.
And just pass it to the next person after this. I've advocated turning off our syslog, but I hear dark comments from people that systemd journal D, as you kind of mentioned in passing, is subject to corruption, and you end up with a binary file that you can't read. How great a danger is that?
There are some narrow cases where, to be clear, I believe these are resolved already, but in the past, we've run into cases where, like, if you immediately shut down or power off without cleanly finishing writing to the journal, we lose some logs. But some of the fixes in the past year should resolve that. Like, we're able to skip over corrupt entries and things like that. As for recent corruption issues, we haven't really seen as many now. So it's hard to, I guess it's hard to quantify the real risk that now that we don't really see them.
I appreciate all of the upstream focus for things you do with systemd and Coro or CentOS. If you were restarting today without any CentOS or systemd or anything in place, would you still make the same decisions with those technologies and what you have built so far? And the second question, from what I understand, most of your services that get deployed on this fleet are containerized. And I don't remember if that's still Tupperware or what that orchestration layer is, but would you still be going with that, or is it tightly integrated into other things you do that is requiring from the bottom-up systemd sort of management?
Okay. So the first question was, if we were to start fresh, would we still kind of make the same decisions as we do now? That's really hard to say, I guess. I don't think there would, even if we started fresh, I guess, assuming like we would still need to have Tupperware, SMC proxy, and all of our other internal infrastructure, it's hard to imagine how we would reconfigure everything, or like if we just plop it down. I don't know. I can't give you that answer. I do know some of the decisions we made to work on a few of our open source projects. Maybe some of them were related to whether we were legally allowed to use some of the other projects and things like that. So no, there would probably be some differences, but as for what it would look like, I have no clue.
Lawyer-driven infrastructure is a real thing, I understand.
I guess if you wanted me to answer the second one.
Yes, sorry, that was the second part.
So we are still using Tupperware. Like I said, it's hard to start over and kind of rip everything out. Still Tupperware, still write our own containerization system. As for what's changed inside the container, we used to run BusyBox. That's now systemd. And it took quite a while, but we did end up upgrading the container OS to also CentOS Stream 8, and they are also working on their upgrade to CentOS Stream 9 now. And I guess we're moving towards a world where we are able to run more than one service inside the same container. We're kind of moving a little, for some jobs that need like multi-service workloads and stuff like that.
I have so many more questions with nested systemd now, but does anyone else say?
On the systemd UMD, could you comment more on how responsive it is compared to the kernel UMD? Is it able to capture processes that are gradually increasing in memory and stuff like that?
Sorry, I missed a little bit of the middle. Which component of systemd are you talking about?
UMD, systemd
systemd
UMD.
UMD?
Yeah.
And what do you...
Is it more responsive than the kernel UMD in terms of process that slowly grow in memory and other parameters?
Oh, okay. So the question was, is systemd UMD more responsive than the kernel killer? I would say not necessarily. We do have like intervals of polling, which I guess are not necessarily faster than what the kernel can do. But it's very different because, the kernel killer has a bunch of stats that it's looking at, and UMD has like a completely different set of stats that it's looking at. So they respond to kills in different ways.
Interested in this idea of systemd BPFD. It certainly seems like using the service infrastructure that systemd has to conditionally load BPF programs depending on the state of the system or associate them with targets could be really powerful. I don't know, for example, if systemd has a language to express start this service if another service has failed. I mean, that's the type of condition where you might want to load additional testing programs. I'm just curious if that's the sort of use case maybe that people are interested in for systemd BFD, or is it mainly loading profiling programs at boot or what?
So systemd BPFD, well, so the original idea is like kind of spun out of the needs for like BPF program management. But that's not what systemd BPFD is going to do. It's currently only focused on like auditing and logging BPF programs. In terms of like doing operations on failure, systemd should already have that already, and you are able to connect different BPF programs to systemd services as well. So you know that specific case you described, it can be workable in the current systemd model already.
Hi. You mentioned most of your machines are homogeneous, and you mentioned GPUs as being something that is changing this. I was wondering, what are the challenges that you're seeing, and what are solutions that you're coming up with managing large fleets of GPUs, especially when you have multiple GPUs on the same hardware?
Oh my gosh, I had the foresight to make some bonus slides. So I didn't want to, you know, kind of ruin the potential for any questions like this. I actually got a similar question at All Systems Go when I first gave this talk. And it's related, like any interesting stuff that came out of systemd with regards to like the GPU fleet and things like that. I think, you know, maybe I naively thought that, you know, it's user space, it's not going to change that much. But there are a lot of calls, especially in the systemd network D related to, you know, talking to the kernel and stuff. And one of the things we did run into is like, hey, there's a 25-second timeout for netlink calls in systemd network D. And in the GPUs, you know, there's like multiple network interfaces, and some of them could take more than 25 seconds. So we would see kind of interface configuration failures there. So I guess it's just like at least the parts that talk to kernel, which are also closely intertwined with hardware, some of the assumptions that we had before are starting to break.
Okay, thanks.
So this is kind of a more general question about systemd. I've noticed that it seems to have a design philosophy of trying to make things easier to configure, like in terms of security, there's sandboxing, there's SEComp, there's some network management. One of the notable things that can be really difficult to configure that seems to be kind of left as an exercise to the reader is mandatory access control. Do you have any comments there?
Mandatory access
Like
control.
SC Linux or AppArmor or SMAC or any of those.
Oh. Yeah, I don't really have any comments on that.
Okay,
I think
thank you.
I used to work on security. It can get kind of gnarly in terms of coming up with the one configuration that works for everyone. And I think while systemd is kind of making some strides, at least in like the secure boot areas, yeah, I don't think we really touched the other parts.
Okay. Just curious if that was an explicit decision or if that you were aware of or not.
Any other questions? Great, thank you.